Howdy, this is Team 14's DSTR presentation, codename Rover. Team members include Eric Kitten and Ashlyn Henson, who will cover the mechanical subsystem, and Kimberly Brannon, as well as myself, Tyler Ott, who will cover the control subsystem. Rover was designed to be a mobile, wireless platform for a multitude of uses with plenty of room to customize everything from design to onboard sensors.
For the portion of the mechanical subassembly, we first start with the fabrication. Figure 2 shows the aluminum materials measured and cut to the specifications for the rover. We noticed that the aluminum was a good material to work with, as it is malleable yet durable, but it did lack forgiveness and milling. We found that the drill bit would slip fairly easily when putting holes into the leg, and we had to clamp the leg down to make sure there was no slippage. Moving on to the chassis construction, Figure 3 shows a chassis with aluminum rods used conjointly with the 3D printed parts to produce the structure for the rover. We learned during the assembly that the holes drilled into the plastic to receive the rods were a little bit too small. This resulted in a lot of time spent filing and forcing the rods into place. Though we know that they are supposed to fit snug, it did result in some parts of the chassis to crack. We would prefer if the holes were made to the exact diameter so that it would be easy to position and then glued together with some form of epoxy. As for the legs, Figure 4 shows one of the completed of the 4 legs. These are to be attached to the chassis, which will provide the stance for the rover and its means of transportation. Again, the aluminum shafts were difficult to insert into the motor coupling and could be improved with more room for insertion and epoxy to secure.
For the leg and chassis connection, Figure 5 shows the connecting of the legs to the chassis by the U-links and the V-links. The aluminum frame was not to be secured too tightly to the links or the leg would not be able to rotate around the rod. We would have liked to have been provided some washers to put between them so the torque of the screws would not limit its mobility. For frame support, Figure 6 shows how the frame support is connected to the leg and the chassis of the rover. This stabilizes the posture of the rover and helps support the flexibility of the rover's legs. We learned that this component is most effective when the plastic supports are free to move along the bolt slightly. Tightening too much makes the frame too rigid. Figure 7 shows the completed product of the mechanical subassembly for the rover. The rover will now be ready to be transformed to the final product upon completion of the control subassembly. We learned that the hardest part of the mechanical assembly is the lack of compatibility between parts. To fix this, the parts should have a tighter tolerance.
For phase 1 of the control subassembly, we created the sled using a piece of particle board. At the top you can see some slits where the launch pad will sit snugly. In our case, the slits are slightly too big, so the launch pad will wiggle around if rover is impacted too much. In Figure 9, you can see the H-bridge configuration, which is a part of phase 2. From here, we were able to wire the motors into the output part of the power board, which is highlighted in orange, allowing us to then control our rover's speed. At the bottom, I'm highlighting in green where the battery pack was placed into the power board to supply power to our motors and to our launch pad. In Figure 10, you can see this launch pad, and I am highlighting in blue where the analog input pins were used to input the signal into our power board, which was then transferred to our motors. Lastly, for phase 3 of the control subassembly, we attached the battery pack, which can be seen in Figure 11, to the bottom of the frame. We learned from all of this that it would be good to test the H-bridge and the motors before assembling them all together. That way we could figure out if we have a faulty H-bridge or if any of the motors were faulty, and therefore wouldn't have to disassemble all the mechanics. Lastly, we learned that the shape of the sled is cumbersome due to the fact you cannot easily access the H-bridge, meaning that if any of the wires were to come loose or there was some faulty wiring, you would have to disassemble the whole control subassembly in order to get to them.
As you can see from the video, Rover is currently fully assembled, integrated, and functional. However, based on the results from the first field test, there are still enhancements we plan to make. By refining the code, replacing the H-bridge, and modifying the wheels with tape, we hope to have even better results during our next test. These are the individual contributions made by each team member. We would also like to thank Dr. Villarreal and Dr. Morgan for the opportunity to participate in this curriculum. Thank you.